Today we are going to learn about mastering PyTorch DataLoader for efficient data handling. You will gain skills in optimizing data loading, setting up DataLoader with custom datasets, and implementing data augmentation for efficient data processing in deep learning projects.
Welcome to our video on mastering PyTorch DataLoader for efficient data handling. In this video, we will explore how to optimize your data loading processes using PyTorch's DataLoader, which is a crucial component for training deep learning models quickly and effectively. We'll delve into setting up a data loader with custom datasets, discuss the impact of batch size on performance, and explore DataLoader's multiprocessing features for speed enhancements. Additionally, we'll cover data augmentation within DataLoader, strategies for handling large datasets, and common issues you might encounter while setting up your data loader. By the end of this video, you'll have a solid understanding of how to leverage DataLoader for more efficient data processing in your projects.
The PyTorch DataLoader is a powerful utility that helps streamline the data loading process for your deep learning models. At its core, the DataLoader is designed to simplify the process of feeding data into your neural networks by taking care of most of the boilerplate code involved in data preprocessing. The two main components of the DataLoader are the dataset and the sampler. The dataset provides an abstraction for accessing your data, whether it's from files, databases, or other sources, and the sampler determines the order and manner in which data is fed into the model. What makes the DataLoader stand out is its flexibility. It can handle varying data formats and is highly customizable to suit the specific needs of your project. By integrating seamlessly with PyTorch models, the DataLoader ensures that data is efficiently batched, shuffled, and transformed, making it an essential tool for any PyTorch practitioner.
Setting up a data loader with a custom dataset involves creating a class that inherits from PyTorch's dataset class. This custom class must implement two essential methods, _len_ and _getItem_. The _len_ method returns the total number of samples in the dataset, while _getItem_ takes an index and returns the corresponding data item. This structure allows PyTorch to access data efficiently, even in complex data scenarios. Additionally, you can incorporate data transformations using PyTorch's Transforms module. These transformations can include data normalization, resizing, or data augmentation, and are applied on the fly during data loading. Once your custom dataset class is ready, it integrates seamlessly with the data loader. By specifying your dataset class, batch size, and other parameters, the data loader can handle data shuffling, batching, and parallel processing, significantly reducing the complexity of data handling in your deep learning project. The batch size is a critical parameter when setting up your data loader, as it determines how many samples are processed before updating the model's weights. Larger batch sizes can speed up training because they make better use of your hardware's parallel processing capabilities. However, they also require more memory, which might not be available on all systems. Smaller batch sizes, on the other hand, might slow down training but can lead to better model generalization because they provide more frequent updates with diverse data. Finding the right batch size is often a matter of experimentation and depends on the specific hardware and dataset you are working with. An optimal batch size balances training speed and memory usage while maintaining or improving model accuracy. It's important to monitor the impact of different batch sizes on your model's performance and adjust accordingly to achieve the best results.
One of the key features of the PyTorch DataLoader is its ability to utilize multiprocessing to speed up data loading. By setting the num_workers parameter, you can specify the number of subprocesses to use for data loading. Multiprocessing can significantly reduce I/O bottlenecks by allowing data to be loaded in parallel, thus improving data throughput and reducing training time. However, there are considerations to keep in mind when using multiprocessing. The optimal number of workers depends on the specific hardware and the nature of the data being processed. Too many workers might lead to excessive context switching and reduced performance, while too few might not fully utilize the available resources. Experimentation is key to finding the right balance. Additionally, some datasets or transformations might not be compatible with multiprocessing due to issues like non-serializable objects or shared state. In such cases, it's important to carefully test and debug your data loader configuration to ensure smooth operation. Data augmentation is a technique used to artificially expand the size of a training dataset by creating modified versions of existing data. This is crucial for preventing overfitting and improving the robustness of your model. In PyTorch, data augmentation can be implemented within the data loader using the Transforms module. Transforms allow you to apply a variety of augmentations, such as rotations, flips, and color changes, on the fly as data is loaded. This means that each epoch can potentially see a different version of the data, enhancing the model's ability to generalize to new, unseen data. To implement data augmentation, you can define a series of transformation operations and pass them to your custom dataset class or directly to the data loader. Combining data augmentation with data loader's efficient data handling capabilities allows for a streamlined and powerful approach to improving model performance. Handling large datasets is a common challenge in deep learning projects. Large datasets can lead to slow data loading times and increased memory usage, which can hinder model training. The PyTorch DataLoader offers several strategies to address these challenges. One approach is to use efficient data loading techniques, such as batching and shuffling, to minimize the time spent waiting for data to be available. Additionally, DataLoader supports distributed data loading, which allows for parallel loading of data across multiple devices or nodes, significantly speeding up the process. To optimize memory usage, you can leverage techniques like data compression or on-the-fly data generation, reducing the memory footprint without compromising on data quality. By carefully configuring the data loader, you can efficiently handle large datasets, ensuring that your deep learning models are trained quickly and effectively. Debugging data loader issues can be challenging, especially when dealing with complex data or multiprocessing configurations. Common errors include data format mismatches, where the data being loaded does not match the expected format, and multiprocessing issues, such as deadlocks or excessive memory usage. To effectively debug data loader problems, it's important to start by isolating the issue. Check the custom dataset class for any errors in the len or getItem methods. Ensure that data transformations are applied correctly and that all dependencies are properly imported. When using multiprocessing, carefully monitor the number of workers and adjust if necessary to prevent excessive context switching or resource contention. Additionally, review any error messages for clues and consult the PyTorch documentation and community forums for guidance. By following these best practices, you can efficiently identify and resolve common data loader issues, ensuring smooth data handling for your deep learning projects.
To maximize the efficiency of the PyTorch DataLoader, it's essential to follow best practices for setup and usage. Start by optimizing the data loader configuration to match your specific project requirements. Choose an appropriate batch size that balances training speed and memory usage, and experiment with different values to find the optimal setting. Leverage data augmentation to enhance model robustness, applying transformations that are relevant to your dataset's characteristics. When using multiprocessing, carefully select the number of workers to avoid resource contention while ensuring efficient data throughput. Additionally, maintain code readability by organizing your data loader setup logically and documenting any customizations or transformations. By adhering to these best practices, you can streamline your data handling processes, ensuring that your deep learning models are trained efficiently and effectively, with minimal overhead or complexity. As we conclude this video on mastering PyTorch DataLoader for efficient data handling, let's recap the key concepts we've covered. We've explored the importance of efficient data handling in deep learning, discussed setting up data loader with custom datasets, and examined how batch size impacts performance. We've also delved into data loader's multiprocessing capabilities, data augmentation, and strategies for handling large datasets. Throughout this video, you've gained valuable skills in optimizing data loading processes, which are crucial for training deep learning models quickly and effectively. We encourage you to apply this knowledge to your projects and continue exploring PyTorch's extensive resources for further learning. Thank you for joining us, and we wish you success in your deep learning endeavors.